the elevator and Newton's second law of motion. I'm going to solve at the same time problem number 13 and problem number 14. They are very similar, but they are opposite. To illustrate this, on problem 13 is related to a man, and problem 14 is related to a woman. And problem 13 is talking about accelerating upward, and 14 accelerating downward. So those two problems, they are kind classical problems for this section when we study Newton's second law of motion. And I'm going to side by side compare how to solve the problem about the elevator. Okay, so here is a sketch of a diagram with a story how goes for each one, how go for each problem. So in the first one says 13, this is 13 and this is 14. 13 says that a 60-kilo man stands on a scale. So this is the data table, 60 kilos. Stands on a scale on an elevator that is accelerating upward at 3.2 meters per second square. What does the scale read? So this is the scale. So this is the man on the scale inside an elevator. So the elevator is suspended. We have several cables. We have a system of pulleys. But this doesn't matter for our problem here. What does matter is that it's going upward. So that is going to be our positive reference. That's how the motion is going. It's accelerating upward. Now, we need to draw a free body diagram on the man. So the man is on the scale, which means that even though the elevator is suspended, but the man is standing on a surface, is pressing down a surface. So this man has a normal force. And because the man has mass, the man has a weight, which is Fg. So the two forces acting on this man is the weight and the normal force. Now, notice that the normal force in this case is greater than Fg. And why is that? Because this system is unbalanced, is not in equilibrium. Before, when we solve problems about friction, and friction is related to normal force, yes, they were in equilibrium. We assume they were in equilibrium, but this time they are not. There is an acceleration going on. So, how are we going to solve this problem? We got the reference going, which is up, and this is a very quick free body diagram to represent the forces, and we are using our Fnet. So we know that our Fn is positive because that's the direction that is going, and our Fg is negative because it's opposite of the direction. Now, let's stop here and let's talk about the problem number 14, which states the woman with 45 kilograms, she stands on the scale just like the man is doing, but this time the elevator is going downward. So here, the woman stands on a scale in an elevator accelerating downward. So that is the reference. Now, downward here is positive. Upward here is positive because that's the direction of the motion. The direction of the motion now is downward. So that is our positive. You see the changing? So the acceleration downward is 2.75 meters per second square. We have acceleration of gravity, which is both our acceleration, but this acceleration never changes. This is a controlled acceleration, and is looking for the reading on the scale. Now, the scale actually is reading Fn. Why is that? Because you are pressing down the scale And the scale has a system of springs and is pressing up as a normal force. But because the system is not in equilibrium, so those forces are not equal. Okay, so we are going to do the same equation setup. F net is equal Fg minus Fn, because now Fg is positive because it's the same direction of the motion, and Fn is negative because it's opposite direction of the motion. Now, the rest is pretty straightforward. We are going to start right here. So our F net is MA, Fn is what we want to calculate, and Fg is Mg. So, and then we want to eliminate this. So we do plus Mg because this is minus, and plus Mg. So likewise, on the other side, we have the same idea. So this is what we want to calculate. And we F net is MA, Fg is Mg, and Fn is what we want to solve. So now we need to eliminate Mg by subtracting both sides by Mg. So this goes, cancel out. And now we have, on both cases, this one, what is left is Fn is equal MA plus Mg, because here nothing else is left on this side of the equation. So Fn is equal MA plus Mg. On this side, our Fn is negative, and this is canceled out, and we have MA minus Mg. So in this case, because Fn is negative, we are going to multiply the entire equation by minus 1. So now we change the sign of Fn. We change the sign of Mg. Mg was negative, now it's positive. We change the sign of MA, which was positive, now it's negative. Now we do our substitutions with the values that we have on each table. So our mass for the man is 60, the acceleration is 3.2, and acceleration of gravity is 9.8, and that is the force that is read on the scale, 780 newtons. We call apparent weight, which is not the real weight. The real weight of the man is Fg is equal Mg, which is 60 times 9.8. So the real weight of the man is 588 Newton. But because the man is in an elevator that is accelerating upward, so his weight on the scale is going to be greater. Now, for the woman, we make our substitution. The mass is 45, G is 9.8, acceleration is 2.75. So the weight of the woman when the elevator is coming down with that acceleration will be 317. That's actually the apparent weight, it's not a real weight, is less because when you come down with an elevator, you can feel that you are lighter. So the real weight of the woman is Fg is equal to Mg. Her weight is 45 kilos times 9.8, which is 441 newtons, which is more than the one that we read when she was in the elevator.